Hello guys, welcome back to Math Zone African Motives. Still working on our electrotechnics and 4 revisions. In this case, we shall be working a basic introduction and working also with question papers at the same time after the introduction of this part, working on the resistivity and also to know about the temperature coefficient of resistance in our electrical machines. What you're going to start with, or the basic part that you're going to start with, is on the resistivity in this case. So we have got the resistivity. That is actually, where is this part of resistivity coming from? The resistance part. So the resistivity, we are simply referring to the specific resistance of the conductor. This is the specific resistance of a conductor. So we are talking about the specific resistance there. The specific resistance of a conductor. It actually gives us the difference between for different conductors. We can tell from that resistance, that is the resistivity of the material. Each and every material has got its own resistivity that is going to work with, which is measured in ohm meters like this. So calculating our resistance from the resistivity, it follows that the resistance of a material now is going to be the resistivity times the length over the area in this case. So the resistance is proportional, directly proportional to the length, and this same resistance is inversely proportional to the area. And this resistance, as we know, measured in ohms. So like I said, this is the resistivity of the material, which tells us the type of material that we are working with in this case. So that's the resistivity of the material in this case, of the material that you are working with. And like I said, measured in ohm meters. Here we are talking about the length of the conductor, in this case measured in meters. Then its cross-sectional area, here we are talking about its cross-sectional area being measured in square meters. So this is all you need to understand about how to calculate the resistance of a certain conductor, and also to note that the area, when given diameter, our area is going to be taken from pi d squared. From the diameter, we are going to have pi d squared over 4. That is the area. Like I said, our area is supposed to be in square meters. And also on this area, sometimes they might give us the area, but in different units. So we need to know the conversion part. If we are given our area in square centimeters, let's say about x square centimeters, we are supposed to have this area in square meters. You multiply by 10 to the exponent of -4. That is to convert this area to square meters. If you are given the area in square millimeters, you multiply this by 10 to the exponent of -6. That is to convert your area to square meters. So this is a conversion that is happening for our area from square centimeters to square meters. You multiply the number that you are given times 10 to the exponent of -4, the number that you are given in square millimeters times 10 to the exponent of -6. You now have your area in square meters. So with this whole information, we can be able to attempt our questions. This is what we just need to understand about our resistivity and the resistance of a certain material. Here we are given the first part of our question. We are going to focus on the resistance, not on the induced EMF. We are just going to focus on the resistance. We are given that a coil, it has got 50 turns of a conductor. And with a cross-sectional area, take note, we are given in square millimeters, and the mean length of 120 millimeters per turn has got an inductance of, all right, so in this case, we do not want to focus about the inductance. We want this question about calculating the resistance of the winding. If the specific resistance of the conductor is, we are given the specific resistance, which I referred to as what? As the resistivity of the material. So we are going to calculate the resistance, and also take note our area being in square millimeters, meaning to say we are going to multiply by 10 to the exponent of -6 to convert this area to square meters. These are some of the things that you are supposed to take note when you are given your values. So that is going to be the given information. Here we've got the number of tens of 50 tens in this case, and we've got area. So this area is going to be 0.2 times 10 to the exponent of -6 in square meters. Remember the conversion. Then on this part, we are given the mean length per 10. This is the mean length per 10, per given 10, each and every 10. We are going to have 120 millimeters each and every 10. So it means the total length is going to be the length that we are given in millimeters, which is our mean length of 120 millimeters times the number of tens. You multiply to the number of tens. There are 50 tens that you are given. So this gives us the actual length that is going to be 6,000 millimeters. So you are going to obtain 6,000 millimeters. But like I said, from our formula, we are supposed to have this in meters. Divide by 1,000, you are going to obtain 6 meters, or multiply by 10 to the exponent of -3 to remove the millimeters. So we are given also that we are supposed to calculate the resistance. Remember, our question here is to calculate the resistance of the windings. If the specific resistance of the conductor, that is the resistivity, is given as 0.025 micro-ohm meter. So micro, that's times 10 to the exponent of -6 ohm meter. So what is going to be the resistance of this material in this case? So as we stated from our formula, we said the resistance of a conductor is going to be resistivity times length over the cross-sectional area. So if we are to take note here, we have got the resistivity of the material of 0.025 times 10 to the exponent of -6 times the length of 6 meters, everything over the area, which is going to be 0.2 times 10 to the exponent of -6 in square meters. We are supposed to have this in square meters. So if you are to simplify, you're going to obtain your resistance as 0.75 in ohms in this case. So that was our question, to calculate the resistance of the given material. That is how you play around with your information. Let us check another question again on our resistivity. We are given the cross-section, calculate the cross-sectional area. We are supposed to calculate the cross-sectional area of a 74-meter long copper. In this case, we're dealing with a copper that has got a length of 74 meters. In this case, so it has got a length of 74 meters. Conductor that will be able, take note, that will be able to carry a current. So this one, it can only a current of 16 amps. So for the current of 16 amps with a maximum allowable voltage drop of 6.4 volts across the conductor. So we also have the voltage across the conductor of 6.4 volts. Take the resistivity of copper to be this value. So we are given the resistivity of copper in this case. We are going to take the resistivity of copper, which is going to be that's 0.017. Take note here, this is micro-ohm meter, so that's micro times 10 to the exponent of -6 in ohm meters. All right, so with this information that we have, what is going to be the area in this case? All right, so take note, we said from our resistance, this is L over the area in this case. So meaning to say, we can have the area from our formula, but we need the resistance. We can even make this to be the subject of the formula. That is going to be R times A, which is RA is equal to resistivity times the length. So to find the area, we divide by the resistance here. So that means our area was supposed to be the resistivity times the length over the given resistance in this case. But if we are to check, we do not have the resistance. We've got the resistivity, we've got the length, but we do not have the resistance. So where are we going to obtain the resistance? We have got the voltage and the current that we are given in this case. So from the voltage and current, we know that voltage is current times the resistance. So therefore, the resistance there is going to be voltage over current, which is 6,4 over the current of 16. So there we are going to obtain, sorry for this, we need the resistance in this case. So our resistance is going to be voltage over the current in this case. So that's our resistance at the end is going to give us what? All right, so let us just check on our calculator. This one, what we're gonna have, it's 6,4 divided to 16. So that's divided to 16, which is 0,4. So we are obtaining 0,4 ohms. So with this resistance that we have, this is the one that you're going to substitute in place of R to obtain our area, which is going to be the resistivity of 0,017 times 10 to the exponent of -6 times the length. In this case, we have got 74 over the resistance, that's 0,4. So this one is going to give us our area, knowing that our area is measured in square meters in this case. So that means all we're gonna need in this case is our calculator to simplify this value that is going to be 0,017 times 10 to the exponent of -6. Then we're gonna multiply to 74 over 0,4. All right. So that was going to give us 3,145. All right. So we are going to obtain 3,145 times 10 to the exponent of -6 in square meters. But I want you to understand what I explained before. Remember, I said for you to convert an area that is in square millimeters to square meters, you multiply that number by 10 to the exponent of -6. So it means if you see times 10 to the exponent of -6, it means that area is directly in square millimeters. So that means we are going to obtain our area as 3,145 square millimeters. We are simply converting this back to it where it was before. Or you can just leave your answer in square meters as it is, or you can write it in square millimeters. So that was the idea. Sometimes you'll be given another information that you're supposed to use to calculate the resistance from. Then you use that resistance now to calculate whatever that you're given by manipulating your formula in this case. So here we're supposed to manipulate our formula. We make the area the subject of the formula, then we substitute our values as we are given. So let us check another part, which is now on the temperature coefficient of resistance in this case. So before we check these questions, we just need to have a basic understanding. What is it that we're talking about? The temperature coefficient of resistance in this case. So we have the part of the temperature coefficient. That's the temperature coefficient of resistance in this case of resistance that will be of a certain material. So we are simply referring that this is the temperature coefficient of resistance of a substance is the increase in the unit resistance per unit temperature. So this is simply the increase. Let us have it this way so that we can understand the basic part. The increase in this case, the increase in the unit resistance. So we're gonna have the increase in the unit resistance per unit temperature in this case, per unit temperature. All right. So this is what we are simply having per unit temperature, which is taken from, take note, 0 degrees Celsius. So this is supposed to be taken from 0 degrees Celsius. So that is what we refer to as the temperature coefficient of resistance. So if we are to calculate, let's say, because we are saying it's taken from 0 degrees Celsius, given a condition that our temperature is starting from 0, then the temperature increases. Our temperature is referred to as theta for temperature. We are going to be using theta in this case for temperature. So the temperature coefficient of resistance, which is alpha, not in this case, which is referred as alpha, but depending with at which temperature. So at 0 degrees Celsius, it means theta is equal to 0 degrees Celsius, which is temperature. The temperature coefficient must correspond at 0, which is our theta naught in this case is supposed to be the theta at the given temperature. If it is 0, then this is going to be theta naught. All right. Having at 0 degrees, it means we can even calculate the resistance that can happen after a change in temperature, after the temperature is increased. So let's say our temperature is increased from 0 degrees Celsius at a specific, the temperature coefficient of resistance at 0 degrees Celsius, it is increased from this value to T, which is the final temperature in this case for that consideration. So T representing our final temperature. It means we are going to obtain our total resistance RT as R naught, that is the resistance at 0 degrees Celsius, plus the resistance at 0 degrees Celsius times the temperature coefficient of resistance at 0 times the temperature that has increased to, that is our final temperature from 0. That is the formula that we are supposed to apply on a condition that we started from 0 and increased to a certain temperature, talking about the same material. The same material increased from 0 to a certain temperature T, whereby this RT is the resistance at this temperature. Remember, I said to T, which is our final temperature in this case. But on a condition that we have got initial temperature as theta, not at 0 degrees Celsius. So this, it represents at 0 degrees Celsius. So given a condition now that our temperature theta is not at 0 degrees Celsius, it is starting at another value, at another particular temperature, we are going to have our formula this time given as RT is equal to R theta. So our formula is going to be R theta into 1 plus. Actually, this is the same formula that you're supposed to use, but it's good to obtain this now with a change in temperature. All right, so we're going to have the temperature coefficient of resistance at the given temperature, then into the change in temperature. So the change in temperature is given as the final temperature minus theta, which is our initial temperature in that case. So this is the formula that we are going to use to calculate the total resistance, whereby now RT is the resistance at the final temperature. The resistance at the initial theta is our initial, our starting value. This is our initial temperature. Your initial temperature where you are starting from. If it is starting at 20, that's your initial temperature theta, this one, our initial temperature. T is the final temperature. So meaning to say you're going to subtract final temperature minus initial temperature, that is the change in temperature, with the temperature coefficient of resistance at that initial temperature. This is the formula that is best to use. So each and every formula is best to use on its own condition. There's also this formula that is best to use on a condition that you are going to obtain a condition that you are given different temperatures, different temperatures in this case. So this is another formula that is important. You are given different temperatures in this case. These temperatures that you are given, they are corresponding to their own resistances, but you are given the temperature coefficient of our resistance at 0, but given, all right, but given the temperature coefficient of our resistance at what? At 0 degrees Celsius. What is going to be the condition? What I'm trying to say is that you'll be given a certain resistance at a temperature of 20 degrees Celsius. You'll be given a certain resistance at a temperature of 50 degrees Celsius, whereby we're supposed to apply this condition because our initial temperature is not 0. But they are not going to give us the temperature coefficient of resistance at the temperature, at the initial, because they are supposed to give us at the initial temperature. They won't give us this. They will give us the temperature coefficient of resistance, this one. They will give us at 0. That is the most important part. You'll be given the temperature coefficient of resistance at 0 degrees Celsius. The best formula that you're going to use on that condition is going to be R1 over R2 is equal to 1 plus the temperature coefficient of resistance at 0 times the temperature 1, which is the temperature corresponds. This is R1, it's from T1. If this is R2, it's from T2, the second value. But they are referred back to the temperature coefficient of resistance at 0. That is the most important part that we are seeing on this formula, that we are referring our temperature coefficient not at the initial temperature, no, but they will give you at 0. This is the best formula that you're going to apply on that consideration. So I want us to see basic questions that you'll be given, like which might include any of these formulas that we have listed, especially this one. But like I said, on a normal condition, this was the formula that you're supposed to use. This one, we can use it because we have the temperature coefficient of resistance at the initial temperature. This one, we are given it at 0 degrees Celsius. That is the difference between these two. So let us check this condition that we are given and we see which best formula to use. We are given, in this case, the field coils of a motor have a resistance of 128 ohms at 22 degrees, take note, at this temperature. After they run at full load, the resistance increases too. So the resistance has changed from where it was to this value. The question is, find the temperature of the coils if the temperature coefficient of resistance is, take note, 0.04 per degree Celsius at this temperature. If we started the motor at 22 degrees Celsius, we were supposed to be given the temperature coefficient of this at 22, but they are giving us the temperature coefficient at 0 degrees Celsius, not corresponding to the one that we started, because this is our initial temperature. So we are supposed to have the temperature coefficient of resistance at that particular temperature that you are given, which is the initial, just like what I was explaining here to say, if this is initial temperature, you are supposed to be given the temperature coefficient of resistance at that temperature. But they are giving us not at the corresponding temperature, but they are giving us at 0 degrees Celsius. So which formula is best to use? We go back to this one that I was explaining. You are given different temperatures, but the temperature coefficient of resistance is given at 0 degrees Celsius. This is the best formula for you to consider. So meaning to say, on your consideration, we are supposed to be thinking of this formula in mind, because the temperature coefficient of resistance is given at 0 degrees Celsius, whilst our temperatures are not at 0 degrees Celsius. So our formula is going to be R1 over R2 is equal to 1 plus the temperature coefficient at 0 now times the first temperature, 1 plus the temperature coefficient times the second temperature. So on our given information, it means for the initial temperature, this is our R1. So our R1 is going to be 128 ohms at T1, which is the initial temperature of 22 degrees Celsius. Then after the run, the resistance has increased, meaning to say we've got R2 at 136 ohms. We do not know the temperature that is going to correspond. Given the temperature coefficient of resistance at 0 degrees Celsius, which is going to be 0.004 per degree Celsius. So that is the information that we are given. So we can simply substitute into our formula so that we can calculate T2 in this case. That is R1, it's 128. So we're going to have 128 over R2, which is 136. So this is equal to 1 plus the temperature coefficient at 0 degrees Celsius, which is at 0 degrees, that is 0.004 times T1, which is 22 in this case. All right, everything over 1 plus the temperature coefficient at 0 degrees Celsius times T2 in this case. So remember, T2 we do not have. This is the one that we are supposed to calculate. So we can play on our calculator, do the cross multiplication. So here, the 128 is going to multiply 1, which is 128 plus 128 multiplies 0.04. So this is going to give us 0.512 T2, which is equal to the same thing. 136 is going to multiply 1 on this side, which is going to be 136 plus 136 is going to multiply this part together, or you just combine it once, all right? Just one and the same thing. So you obtain 11.968. So we can combine, collect our like terms. In this case, that this to the other side is going to be a negative 128. We are going to subtract 128 on the other hand. So that means we are going to obtain 0.512 T2, which is equal to, combine this part, subtract 128, you get 19.968. So to find T2, you are going to divide by 0.152 both sides. All right, so that's going to give us the value of T2 in this case, which was going to be 39 degrees Celsius in this case. All right, so this is how you play around with your information. You check the formula that corresponds to the information. Each and every formula is based on its own. This formula, it's when you are given the temperature coefficient of resistance at 0 degrees Celsius corresponding with the resistance at 0 degrees Celsius. This one, you are given the temperature coefficient at the initial temperature, which is theta, and its corresponding value. But if we are given different temperatures and the resistances that are corresponding to those temperatures, but the temperature coefficient of resistance is maintained at 0 degrees Celsius, this is the best formula that you are supposed to apply, or that is the formula that you are supposed to use on your calculations. I think we are together on this part. Let us check another part. We are given that the resistance of a coil wire increases. So take note, it's increasing from 40 ohms at this temperature to 60 degrees Celsius. Find the temperature coefficient of the conductor at, take note, we are back again, 0 degrees Celsius. We were given temperatures 10 degrees, this and that. We are given different temperatures at 10 degrees, at 60, but we do not see a condition whereby the temperature coefficient of resistance is given at the initial temperature, which was supposed to be given at 10 degrees Celsius. But we are given it at 0 degrees Celsius. So we are back to the same formula that I explained before, that we are going to use the formula of R1 over R2, which is equal to 1 plus the temperature coefficient at 0 degrees Celsius times T1, everything over 1 plus the temperature coefficient of resistance at 0 degrees Celsius T2. That is the best formula. So read the question up to the end so that you see the formula to use, and knowing the formula to use, it is going to be easier for you to collect your information. You know that this is my R1 at the initial temperature of 10. So I've got R1 of 40 ohms, which means our initial temperature is going to be 10 degrees Celsius there. And we are given it increases to the resistance now, which is our R2. That is going to be 48.25 ohms at this temperature, which is T2, 60 degrees Celsius. Then the question is to find, meaning to say we are supposed to find the temperature coefficient of the conductor at 0 degrees Celsius. So we are simply going to substitute our information. R1, that is 40 over R2, which is 48.25. This is equal to 1 plus. Remember, we need to calculate the temperature coefficient, so we do not have this value, but we are given T1, which is 10 in this case, all right? Everything over 1 plus, we do not have the temperature coefficient, but we've got T2 in this case, which is 60 degrees Celsius. So we can play around with our information just like the previous part. We can cross multiply. So the 40 is going to multiply 1 here, which is 40 plus the 40 is going to multiply the whole of this part here. So that's 40 times 60, which is going to give us 2,400 alpha naught, which is equal to the same thing. This part is going to multiply the rest on top. So that's 48,25 times 1, which is 48,25 plus 48,25 times 10, which is going to be 482,5 theta naught in this case. So what we need is to calculate this temperature coefficient of resistance at 0 degrees Celsius. So we're going to collect our terms. We can transpose this to the other hand so that it can be a negative on this part. That's 2,400 alpha naught minus 482,5 alpha naught. And this side, we are going to remain with 48,25. We transpose the 40 to the other side so that it can be a negative on this side here. So simplify, you're going to have 1,917,5 alpha naught in this case. Then we've got 8,25. Remember, this is alpha, but here we are referring it as the temperature coefficient of resistance. So we divide by this value both sides since we are supposed to find alpha. So if you divide properly, you are going to obtain something like 4,302 times 10 to the exponent of minus 3. Remember, it is measured per degree Celsius. So you can even leave your answer like this, or you can write it as a decimal, as an exact decimal. I don't know, it's up to you, but you can just even leave your answer like this. So as you can see, the formula to use is based on the information that you're given. The formula that you're going to use is based on the information that you're given. So we are going to consider another question so that we finish up and see how these questions are given as. All right, so we just have this one here. So on this one, we have got, let us check our question. The field of a current of a shunt connected generator is 4,1 amps. So we have got the field current of a shunt connected, which is the input current, with the initial temperature. Take note, we've got the initial temperature in this case at 20, take note, at 20 degrees Celsius. The generator supplies a full load current, which is going to be at a terminal voltage of 230. Just before the generator is stopped, the temperature of the coil reaches 60 degrees Celsius, which is our final temperature, the 60 here. Calculate the voltage drop. Take note, we are supposed to calculate the voltage drop, which is the change in voltage, if the field current, if the temperature coefficient, this is our most important part here, if the temperature coefficient of resistance at 20 degrees Celsius is, take note what we are given here, the temperature coefficient at 20, meaning to say we are no longer going back to that part that we used to work with, whereby we're given at 0 degrees Celsius. We are given the temperature coefficient of resistance corresponding to the initial temperature. It is corresponding. If you check here, I said whenever the temperature coefficient of resistance correspond to the initial temperature, you are going to apply the exact formula. This was our application here, if you still remember, on this introduction here, where I introduced, okay, where is that part of the temperature coefficient of resistance? It must be, I just hope it's on this one. All right, exactly on this part here. If you still remember what I was explaining here, to say if the initial temperature here is corresponding with the temperature coefficient of resistance in this case, with the initial temperature, this is the best formula that we are supposed to use. We did not start at 0, we started at another temperature. So that is the formula that we are supposed to apply in this case. All right, knowing the formula to use is best, so that you also know how to take this information that you are given. So in general, we are saying the formula that we are going to apply at the end is RT is equal to R theta, that is R theta, the resistance at the initial temperature, all right, into 1 plus the temperature coefficient at that temperature, that you are given into T minus the initial temperature in this case. All right. So on this part, from the given information, what is it that we have? We are given that the input current in this case, so we have got the input current to the circuit of 4,1 amps with an initial temperature, which means we have got initial temperature, which is our theta. Theta represents our initial temperature on this condition. So we are given theta being 20 degrees Celsius. The generator supplies a full load current at a terminal voltage of 230 volts. So meaning to say we've got the voltage affecting here of 230 volts. Remember, as we are focusing on the resistance at the initial temperature. So with the voltage that we have, we are going to calculate the resistance. But we are given that later on the temperature increased to 60 degrees Celsius. So this is T, the final temperature. Remember, here we're talking about change in temperature, final minus initial. So T representing our final temperature, it's 60 degrees Celsius. Calculate the drop in the field current. We need to calculate whatever the change in the field current that we are going to have. We shall see that one. But given the temperature coefficient of resistance at 20 degrees Celsius, that means at 20 degrees Celsius, that is, remember, theta is 20. So that is alpha theta at 20 degrees Celsius. It is given as what? 0,004 degrees Celsius, corresponding with the theta at 20 degrees Celsius. So that is why we are supposed to apply this formula here. So what is it that we are going to obtain from this information that we are given? All right, let us see. Remember, we are supposed to calculate the drop in the field current, not in the voltage, but in the field current, which is the change in current. So as you can see that the change in current simply represents the change in current. It is going to be the final current, that is the current taken at the final current, minus the initial current, which is the current taken at 20 degrees Celsius. And here we have the initial current, in this case, from the information that we have, our initial current, the current is 4,1. But in order for us to have this total current, we must calculate the total resistance. And in order for us to have this total resistance, we need the initial resistance, which is the resistance taken at 20 degrees Celsius. From the voltage and current, we can calculate our initial resistance. Remember that resistance is voltage over current. So this is our initial at 20 degrees Celsius. All right, so we are going to have our R theta as the voltage of 230, which is our terminal voltage, over the input current of 4,1. So that will be R theta is going to be 56,098 ohms in this case. So this giving us the resistance corresponding at 20 degrees. We are talking about at 20 degrees Celsius. So in order for us to have the total current, we need the total resistance, which is, we are going to calculate our total resistance from our formula. We now have the initial resistance at this temperature at 20 degrees Celsius. Our resistance is 56,098 into 1 plus the temperature coefficient of 20 degrees Celsius in this case. That is, we have at 20 degrees Celsius, the temperature coefficient there corresponding at this temperature is what? That is 0,004. Okay, into T, which is our final temperature in this case of 60 degrees, minus the initial temperature where we started from was at 20 degrees Celsius. So that is the whole idea. We calculate our total resistance, which was going to give us something like 65,07368, which was going to be 0.74 in this case in ohms. This is the total resistance, not the total current. Our question was to calculate the change in current. They said it must be the total current minus the initial current. So this is our total current. This is the initial, the one that we already have. And here we are talking about the final current, in this case, the final from our final resistance at the temperature of 60 degrees Celsius. So what is going to be the resistance, the current, because we want the change in current. So the current at the final temperature is going to be the voltage over the resistance at the final temperature. So remember, our voltage is 230 divided to our final resistance, which is at 60 degrees Celsius. That's going to be 65.074. So that was going to give us 3,534 amps. So this is the current corresponding to the final temperature, the final temperature of 60 degrees Celsius. So that means now we can be able to calculate what our question is asking, the change in current, the drop in current. So the change in current, like I said, is the final current minus the initial current in this case. So our final current in this case is the one that we are taking at 60 degrees Celsius, which we calculated 3,534 minus the initial current, that is the current I1, the one that we are given initially here, which is 4,1. So we are going to subtract, thus obtaining the change in current here, the change in current. All right, so that is going to give us, in this case, we are going to obtain a negative, that's negative 0,566 amps. All right, so the negative is simply showing us to say there is a decrease, there is a drop. That is why our question here is saying calculate the drop in the drop. That's a decrease. If it is an increase, it was going to be a positive. So meaning to say this negative here is simply indicating a drop. That's a negative. So thus in conclusion, thus the current in this case, the current dropped by 0,566 amps. When we are writing here now, we are no longer writing the negative because already we are stating that it dropped by. If we are not indicating this statement, then we leave with a negative. The negative is indicating that's a drop that we are having from a certain current that we had to a certain current. It was a decrease. An increase, it is going to give us a positive. The final current is going to be bigger than the initial. But if the final current is smaller than the initial current, it means it's a decrease that is happening. That's a drop, a negative that we see here. It's indicating that our current was decreasing instead of increasing. So that is how these questions be like on your resistance and the temperature coefficient of resistance. All you need is to manipulate your formula into what you're asked to calculate and know the best formula to use. So we shall see other questions as we are revising, checking on our past exam papers and see how do they ask these questions so that we apply our formulas to the questions, because it's not just knowing the formulas, but also how to apply the formulas for a specific question that you are given. The information that you are given gives us the exact formula to use. So we shall see as we move on from our past exam papers in the near future.